Okay, good morning. So it's probably time to start. So today we are very happy to have Professor Ryo Yokota from Tokyo Tech to give us a series of lectures. So in these lectures, Professor Yokota will basically cover the fast multiple methods. So actually, Professor Yokota is definitely the expert in these topics. So he has worked on this field and also the edge matrix algorithm recently. So I mean, he has worked in this area for a long time. Professor Yokota, he has worked on this since his PhD and then in postdoc in UK and US, Boston U. And then he moved to Coast in Saudi Arabia to work on this one. So he made a very famous software called XRFMM. And because of this software, he also won the Golden Bear Prize, which is the top prize in high-performance computing. So this is definitely not easy thing, and this is real honor to his excellent work, his FMM. So I think we will be learning a lot from Professor Yokota's lectures, and I think Professor Yokota designed the course quite well. So we have 2 lectures every day, and then we will have 2 hands-on sessions, so that we can keep our concentration. So 2 hours lecture and 2 hours hands-on every day. Okay, so every day after the course, Professor Yokota will upload the slides so that you can download that. Okay, so during the lectures, please feel free to ask questions. Okay, so if you prefer to speak in Chinese or something, that's okay. I can help to translate that to Professor Yokota. All right. Okay, so that's. Please join me to welcome Professor Yokota.
Okay, thank you very much, Wei Chung, for inviting me to Taiwan. It's actually not my first time in Taiwan. I've been here a couple of times, but it's my first time to be giving a lecture here. It's also not very common for me. I have given lectures on FMMs before, but not such a long one. So this one consists of 20 lectures in total. 10 of them will be actual talks like this, and then 10 of them will be hands-on sessions. So 2 each day for the lectures, and then 2 for the hands-on, and 5 days in total of 20 lectures. And so the first lecture will be on sort of the introduction, what the fast multiple method is, and not too much about the details of how it works, or not too much mathematics in the first lecture. And then the next 50 minutes will be on actually a little bit more of the mathematics, so what the multiple expansion is. So fast multiple method uses multiple expansions. That's why it's called the fast multiple method. And today we'll learn how to construct these multiple expansions and sort of the underlying theory behind it. And I heard from Professor Wang that you have there's a wide variety of levels of the people attending this course. So I will try to keep things very simple. And the math that I will use today is mostly like high school math. There's no advanced skills required to understand today's lecture. And also, since it's a very diverse crowd, I won't introduce too many like computer science words or notions that you may not understand. So this is a very simplified version of the fast multiple method. And what you'll hear now, we will be in the hands-on session later today, we will actually be coding in the code. So if you listen carefully to the lecture now, this will be better for you because you'll be actually writing the code that I'll be explaining now. Okay, so first of all, there are many different algorithms. So fast multiple method is just one particular algorithm that does a certain type of calculation. But in high performance computing in general, or scientific computing in general, has many different types of algorithms. And each application has its own structure. But you can actually classify these into a few groups. So the most historically well-known categorization is where you use this analogy between the seven dwarfs in Snow White and sort of map them to these seven different algorithms. So the one on the far right, dense linear algebra, is things like dense matrix factorization, so like LU factorization, Cholesky. Sparse linear algebra is where you have many zeros in your matrix, and you don't actually have a full matrix. And there are specific algorithms to solve those. And software, oh, thank you. And FFT is another well-known algorithm. It's applied in a lot of signal processing applications, or even in scientific computing if you use things like spectral methods or pseudo-spectral methods, spectral element methods, and so on. It has a very unique type of communication pattern, which makes it difficult to scale on large supercomputers. So before, FFT was like the ultimate algorithm. So you wanted to solve everything with FFT, even fluid dynamics. But nowadays, it's becoming very hard to scale that to the largest supercomputers. Unstructured grids and structured grids, these are a particular type of meshing techniques when you want to discretize a continuous field of some sort and solve a partial differential equation. Then your discretization leads to either of these types of topologies, and each of them have different ways of optimizing. That's why they are categorized into different bins, although they eventually lead to a sparse matrix which you solve. So it's sort of, these two methods have to solve sparse linear algebra, but they're categorized separately because they have unique properties. So if it's just some random sparse matrix that doesn't come from these grids, then there's not much you can do to optimize besides having very clever storing techniques. But if you knew the underlying topology, the geometry really helps you to optimize your code. So this is why it's two separate algorithms shown here. Monte Carlo is sort of a more statistical, it's less deterministic way of doing a simulation. So I'm showing here as a sort of a histogram of these statistical properties. It's sort of used in more, so N-body is used in molecular dynamics, so the study of molecular interaction. But before that, Monte Carlo methods were used. And so these statistical N-body dynamics methods can be found in many areas of science, from the molecular level to the continuum level. And even in astrophysics, you can have different types of N-body methods. So the method I'll be describing today was originally formulated for solving N-body methods. So N-body methods is an algorithm that solves the interaction of N bodies interacting with each other. And it's used in many different applications. So one of the most advanced versions of the N-body algorithm is this fast multiple method. So there's this list of top 10 algorithms of the 20th century that was compiled in the year 2000. So it doesn't include algorithms that were invented after the year 2000, but not too many, like major algorithms have been invented after the year 2000. It seems that these very famous algorithms like FFT, FMM, Krylov subspace methods, maybe, so this may sound unfamiliar to some of you. It's like the CG methods, conjugate gradient methods, or GMRes. They belong to this class of methods. So anything that you use to solve a matrix in an iterative form belongs to these class of Krylov subspace methods. So it's used heavily in many codes. It's like a built-in function in MATLAB. And so you've probably heard of this one, FFT, quicksort, QR method, QR factorizations. So you have here in 1987, so it's a fairly new algorithm compared to the others, the fast multipole method. So it's ranked in one of the top 10 algorithms, and there's out of these different algorithms, the fast multipole method is sort of it has very nice features for calculating in parallel and very asynchronously on these very large supercomputers. So it's sort of a nice algorithm for very large supercomputers. So as a data point for that, I want to back my claim that it's good for supercomputers with this typical, well, it's not typical, this excellent work that was submitted to the Gordon Bell track on SC14, 2014, supercomputing conference, where it was a Gordon Bell finalist, but it didn't make the prize, but still it's an excellent work by the group in Leiden so this work runs on two of the biggest supercomputers that have GPUs. This one has, I think, about 6,000 GPUs, and this one has like 16,000 or more, 18,000 GPUs. Yeah, 18,600 GPUs. So Titan is one of the largest supercomputers in the world. I think the number one is China's supercomputer, Tianhe 2, but Titan is the largest one in the US. And as you can see, this is the speed up you get measured in teraflops, floating point operations per second, as you increase the number of GPUs. So it's like almost scaling perfectly until the whole machine of Titan. And it's very hard to scale like this on Titan because relative to the compute power that the GPUs have, the network is not so strong or well connected. So usually a lot of algorithms have problems scaling to the full machine of Titan, but this one did. And it achieved 24.77 petaflops of mixed precision arithmetic. And so this shows that these types of fast multiple methods or tree codes are very good for scaling, very good on GPUs, and sort of work on these future-looking architectures. So supercomputers are moving more and more towards machines like Titan, and in the future, algorithms like this will eventually have an advantage as we move to more of these GPU-based or accelerator-based type machines. So this is one example. There are more examples. So I mentioned that the previous slide was showing a Gordon Bell submission. So these are the Gordon Bell Prize winners at the supercomputing conference in 15, 14, 2013, 12, 11, going back. And I'm showing which algorithm was being used inside these methods. So I showed the 7 dwarfs. So now I'm showing these best performing application codes of each year and which algorithm they're using. So N-body methods, the FMM type methods, were being used here. This one is a very special submission. Well, this one and also this one. So the one that starts with David E. Shaw. David E. Shaw is has his own company now that builds special purpose computers for drug design. And he used to be a professor, but then he went into the field of finance, made a lot of money, and then came back to academia or science and invests in using his private money in these special purpose computers. And he has built a computer that is so much more faster than the current state of the art that, you know, it sort of has a disruptive effect on the field of molecular dynamics now. Everyone has to be, you know, carefully looking at what these guys are doing, because what they're doing is so much more, you know, advanced in terms of the duration that they can simulate. So people in the field of molecular dynamics can only simulate up to, you know, like microseconds, but these guys can simulate up to milliseconds. That's 1,000 times longer. And note that the delta t, the time stepping size for these simulations, is like 1 femtosecond, 10 to the minus 15. So if he's simulating until, you know, 10 to the minus 3 milliseconds, then he's doing like 10 to the 12 number of steps in a reasonable amount of time. So that's a crazy amount of time steps. And so it's he doesn't necessarily solve a huge problem like these other supercomputers do. He solves a reasonable size problem that's useful in drug design, and he does it really fast. It's like a latency issue that he is solving rather than a scalability issue. And so it's very unique, but it's still an N-body problem. It's classical molecular dynamics. And these submissions also, this is an astrophysical simulation, and also this one is fluid dynamics simulation done with the N-body method. And this one is both astrophysics and fluids done with the N-body. And also this one, again, is the molecular dynamics one. I want to emphasize that the FMM is originally designed for N-body, but it can solve these types of methods that is currently being solved by sparse linear algebra on structured grids. These problems, well, I'll mention in future lectures that the FMM is actually, it has a matrix form. So H matrices is like the matrix version of FMM. And if you view FMM as a matrix, then it's sort of a nice tool for solving these linear algebra problems as well in order n and in a scalable way. So these methods are currently being solved by sparse linear algebra, but they may be solvable with FMM. So if you look at the potential applications that the FMM can solve, it's almost all of these. So it could be on any Gordon-Bell submission if you can have a highly optimized fast multiple method. That's how important this algorithm is, potentially. So the reason why these fast multiple methods work so well on GPUs and these other architectures like FX10 or BlueGeneQ is because of the number of floating point operations it does per byte that it loads. So in any computer, you have the memory, the RAM on your motherboard. Data from the RAM gets loaded into, like the L3 cache, and then the L2 cache, and then L1 cache, and then into the registers, and then it goes into the arithmetic units, the transistors that actually do the additions and multiplications. And it's done, in like sort of a hierarchical way. And the amount of bytes it can transfer when it goes up these memory hierarchy is limited. And if you do more calculations for each data you've loaded, you can get more floating point operations per second out of the same chip. In other words, if you load some data and just do one computation on it and then throw it back out, then it's not being utilized. The whole chip is not being utilized very efficiently. And this is a chart that shows that. So it's called the roofline model. And as the operational intensity of your algorithm increases, first, your performance increases, but you're still memory bound. But you start from like a very low performance in terms of flops per second. But then you increase until you hit a point where all your arithmetic units are already busy. So even if you load more data, there's no arithmetic units that are free. So you can't deliver more floating point operations. So this is like the theoretical limit of the arithmetic operations that you can do per second on a given chip. So you can't do any faster because you don't have enough transistors to crunch numbers anymore. But until you get there, you want to do as many floating point operations per data you've loaded. And if you look at sparse matrix vector multiplication, it's right here. So this dwarf. Stencil code, if you use a high order stencil, maybe here. 3D FFT, somewhere around here. Of course, some of these numbers here, the exact number that it's showing here, can vary depending on the cache size of the machine, because some are sensitive to the cache size. For example, actually all of these here are sensitive, are functions of the cache size. Because the number of flops it does is sort of asymptotically different from the amount of bytes it needs to load. So FMM, M2L is a particular kernel inside the FMM, and P2P is also another particular kernel inside the fast multiple method. It has very high flops per byte. So dense matrix multiplication, DGEM, is known as one of the most high operational intensity operations that you can do on a computer. So things like the LIMPAC benchmark that people run to benchmark supercomputers and rank the top 500 list, they're full of DGEMs, actually. And therefore, that's why you get a very close to theoretical peak performance. But some operations in the FMM have even higher operational intensity than that. So when the trend of future architectures is shifting this sort of point where this thing levels out, this point at which it levels out is shifting more and more this way. So more and more algorithms are becoming memory bound. If it's on this slope, it's memory bound. And this slope region is shifting this way on future architectures. So of course, with 3D memory that we have now, stacked memory, it shifts a little back this way, but that's a one-time thing. So we still have this monotonic trend that the number of flops per byte you want to do just keeps increasing. So FMM has the potential to remain compute bound for the longest time in terms of what the algorithm can offer. Okay, so now going into what the FMM is, what a tree code is, and what a direct n-body method is. So this picture is the simplest way to explain the difference between these three methods. So if you have n bodies interacting with each other, and if you just do it in a very naive way and loop over all the particles, and then inside that loop over all the particles again and calculate the interaction between each other, then that creates a double loop of order n, which means it has the n squared algorithm. You can look at the number of lines in this picture. That's the number of computations it needs to do. So order n squared. And then if you can somehow cluster the far points into larger and larger sort of representations, then the method becomes n log n. This is called a tree code, like this picture shows. The fast multiple method takes it further and then clusters both sides. So it clusters the j particles and both the I particles and creates a tree for both the source side and target side. And so this being order n is very important when n becomes like billions and trillions. So this is the difference between these three methods. I'll be explaining about this one in the following lectures. So this is a very high-level description of what the FMM is. I'd like to give you a few examples of where it's being used. So in astrophysics, each of these bodies, one point can represent more than one star, like a cluster of stars, but still, you want to calculate the interaction of these galactic bodies. So each of them contains a certain amount of mass. You solve the interaction between all those bodies with the gravitational potential. That's like a 1 over r, 1 over the distance type function. And then you get a simulation like this. You can see how these clusters of stars form, which in the night sky you see pictures like this. If you have a nice enough camera, you want to know, how these celestial objects become this shape and this density and this size. And to do that, you can actually run a simulation starting from an initial condition that's representative of the beginning of the universe, and then you can see these things form. There are other types of astrophysical simulations where you start out with the initial condition of the galaxy being this shape and then have two of them collide and things like this, which is what the previous large run on Titan was doing. It was solving the collision of our galaxy with the Andromeda galaxy. So you can do these kinds of simulations very fast if you have the fast multiple method or tree code. And then it's also used in a very smaller scale for molecules. Each of these atoms are bodies, are particles, and they interact with each other with a potential that is the same as the gravitational potential. It's the 1 over r type potential. And so to solve this potential field, you solve the interaction of all atoms with all atoms, and the electrostatic force is induced from everywhere to everywhere. Everyone feels the effect of everyone else. That's why you need to calculate the interaction of all against all. But if you can do that, you can simulate all these water molecules and the protein inside it. And for example, a typical application would be if you had a new drug that had a certain form, you want to see how it docks with certain proteins, and so that you can deliver drugs more efficiently or design new types of drugs even without experimenting, because experiments can be very expensive if you do it 1,000,000 times, but if you do it inside a computer, it's just the electricity that you need to pay for. So at the scales that are too small for people to directly see and to manipulate, or scales that are too big like the galaxies, simulations are very useful because you can't really do too many experiments at those very large or very small scales. But with these tools, we can do it in a computer many, many times under different conditions. And so fast multiple method can be used to solve these types of problems too. A third type of problem is fluid dynamics. Usually you solve fluid dynamics using a mesh, but you can also solve it using particles. These are a bunch of fluid particles. And you can simulate something that looks, this is a simulated calculation. It's in slow motion, so it looks kind of strange, but it's actually being calculated by this kind of particle-based fluid dynamics method that calculates splashes by splashing particles around. And so this is also interaction of these particles against particles. And for incompressible flows, you need to solve a Poisson's equation, which means it's like the same potential again. It's the 1 over r type potential. And you can simulate that very fast if you have a fast multipole method. Again, it's everyone interacting against everyone if you want to solve the incompressible equations. So this is what mathematically this potential looks like. I've been saying 1 over r, but this is what I meant. So r is the distance between 2 points, xi and xj. So let's write this rij. This is equal to vector xi minus vector xj, which is this arrow here. And you take the norm of that, and you get the absolute distance as a scalar. And the potential is a function of the inverse of that. And you need to sum for all the j particles inside. But if you look at what one j particle induces, this is 1 over r. So when r is 0, it goes to infinity, and then it rapidly decays. So if you plot it in 2D, it looks like this. It's like a peaky mountain, like potential. And so this is the potential that it induces. If you take the gradient of the potential, you get the force. So you can take the gradient of this function here, and then you can calculate the force acting on each body. And according to the force, you can calculate the velocity. According to the velocity, you can calculate the x at the next time. And that's how you progress. You calculate f, you calculate v, you calculate x, and then the new x you use to calculate, again, the new potential, and then the new force. So that's how a typical n-body method proceeds. You calculate, you keep incrementing in very small time steps the movement of the points by calculating its force induced on them and moving them according to that force. So to do that, if you have many, many bodies, you want to calculate them efficiently. So here comes the sort of theoretical part, the beginning of the theoretical part of this lecture. So the first step, what do you do? So assume you have these points here with qj charges. So q is, it can be the mass for galaxies or the electrostatic charge for molecules. It's the value that each of these points possesses. So you have a 1 over r potential. So xi minus xj, the distance, and then you multiply the charge to that. And then you sum up all the effects, and then you get the induced potential, ui, at all those points. So consider these as the source points, and these as the target points, and say that these two are far away. So this one is over here, this one is over here. They're far enough that you can actually average, well, you can actually sum up all the points q in this field. So this point is actually at the center of this box here, this center point. You sum everything to the center and say, I have qj prime charges at the center here. So from this target particle, this whole thing looks blurred, and it looks like one big point that has a charge, qj prime. That's the sum of everything inside here. It looks like one big blob, like shown here. And then you calculate the effect of that, qj prime, using the two distance between the two centers of these boxes. So this point here is at the center of this target box here. So you're calculating the distance between the two centers, xi prime minus xj prime, and the distance. And then you say that is the potential that's induced on roughly this entire area. So what you're saying here is ui prime that's induced here is equal to everything here. What I'm saying is everyone is feeling roughly the same effect. So I'm just going to substitute ui prime, that's the potential here, to all the values here. They're all the same potential. It's a very rough approximation, but when this box is very small, and this box is very small, and these two boxes are very far from each other, it's a rather good approximation. It's just a relative issue. It depends on how small this box is compared to the two distances, the distance of the two. And so if you draw a picture of that, the interaction between the two bodies, this actually looks like this. So you're taking all the sources, gathering them into one point, then calculating the interaction between one point against one point here, and then spreading the effect to the other points. This is like the simplest FMM-like method that you can think of. Just average everything in the center, calculate only one equation you need to calculate between the two centers, and then say that everything inside the box is equal to what you've calculated here. This is like step one for the most basic FMM. So we'll do the hands-on coding session starting from this one. We'll actually code this and see how good this works. It's going to give you a roughly correct answer. So it's already, quite good. And it's going to work much faster. We're going to compare the speed to calculating everything against everything with this equation and compare that with doing step 1, step 2, step 3. And then we compare this UI, the approximated one, with this UI that we get by directly calculating. By comparing the two, you can show in the hands-on session the accuracy of this very simple looking FMM-like method. So now we can improve this slightly. So here, this was the particles we assumed that would be very far from each other. This is actually not the case. To make it more applicable to a real problem, what we need to do, so usually what we want to do is we have a box full of points, and we want to calculate all the points against all the points, and not necessarily the two that are far from each other. So how can we make sure that when we calculate the effect of all the particles in this big box against each other, how can we assure that two are far from each other? Well, the simplest solution is to divide the box into many points, and when you're calculating this one, just calculate against these with the approximation, and everything that's close, these ones here, you just calculate with the the direct interaction calculation here, which is the exact solution. So you only use this approximation if you can identify that the boxes are far enough. So you sort of you need to split it into at least 16 boxes like it's shown here. If you only split until 4, everything is still neighbored, so you can't really do the far. So when you split twice, then you have these far ones. So at this level, you can actually split into the near and far. So this blue box I'm just showing for this one, but you actually need to loop over all the boxes and consider them as the blue box, and then calculate the appropriate red far boxes, and also combine that with the solution of the near boxes. So this is step 2, near far decomposition. So in the hands-on session, we will do, after we finish this one, we will try to code this thing. So what you need to do is you need to divide the domain into like these small boxes, and then you need to figure out how to calculate which box against which box. If you number them in a clever way, it's very easy to identify from that number which ones are far and which ones are near. And if you number these points in a clever way, it's very easy to identify from the number of the box which particles are inside that box. It involves sorting these points so that they are continuous inside each box. Initially, they might be randomly positioned, so you need to sort them so that it goes like 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, 11, 12. So we'll do this in the hands-on session, how to organize the points, and then call this one for these boxes, and call this routine for these boxes. And then we need to sum up all the answers that we got here, add them to the ones that we get here, because it's the sum of the near and far. It's the effect of everything. So it's the effect from all of these and also all of these. So you need to add the answer to the UI at the end. And then we'll compare again against the case where you calculated everything against everything. So once we can do this comparison, now this is, it can be applied to a real problem. Now actually, even with this very simple two-step, the second step, you can already calculate for a real molecular dynamics simulation a very rough answer, but still, you can already calculate something that's close to the answer you want, and it's probably faster than calculating everything against everything directly. Say you had 1,000 points, then that's 1,000 by 1,000 calculation if you do it directly. If you do it this way, you're calculating for a smaller subset of the points with this one, and this one you're only calculating against 2 points every time. So it should be much faster, but not so much different because you're basically saving, you still need to do this part directly. You're not saving much. So the problem with this one is that you're only decomposing the domain with one level. There's no hierarchy here. So the next step after this one, what's the logical next step to take? Of course, we introduce more levels in the tree. So we divide them further and further until they become smaller and smaller. So if you have a big problem, if you have like 1 million particles, you can use a technique, just make the tree deeper. And as long as you have a constant number of points at the bottom, at the smallest box, this method is order n. The reason is because when you do this calculation here, if the number of particles per box is constant, regardless of how many you have in total, if you can make the tree deep enough, you can always have a constant number of points at the lowest level of the tree. And you will do order 1 calculations for each box. You have n boxes at the bottom of the tree. So this is order n. So now think about this stage. When you have many boxes, you calculate at the center the average, and then from each of those averages, you just sum up to get the bigger box average. You do this for as many number of nodes you have in the tree again. So for any tree, the number of nodes in the tree is still order n. So this calculation here is order n. Now, when you want to calculate the points against each other, you sort of form this hierarchical type of interaction list. So for the points here, you interact the big box against the big box. So, and for the smaller ones here, shown in the light green, you calculate against these boxes. And further down the tree, you calculate against these boxes. And then at the bottom, you calculate against the particles directly. So at each level, think of how many points you're interacting with at each level. It's a constant. So this is this many. At this level, it's also a constant. It doesn't depend on n. It's order 1 number of points. And here, again, it's an order 1 number of points that you're interacting with. And so it's always order 1 points that you're interacting with for each node in the tree. How many nodes in the tree do you have? You have order n nodes. So it's order n nodes times order 1 boxes of interaction. So it's order n times order 1 means this calculation here is also order n. And going down the tree, it's the same thing. You calculate this against this. This side was order n, so going down, it's the same thing, order n. And when you distribute, again, these points to the ones here, it's again order n, because this side was order n, and it's sort of symmetric. So now you know that each stage, step 1, 2, 3, 4, 5, is order n. So the condition is, if you can make the number of points per, smallest box in your tree constant, make the tree deep enough when your problem size is large, then this method is already an order n method. The problem is, it's not very accurate because, you're not doing a very accurate calculation here. You're just summing up the effect. And then here, you're just assuming that everything is equal to the center. So again, you're assuming, say that this point here is I prime prime, and these points here are I prime. You're saying that the effect on this one is equal to these, and the effect on this one is equal to these. So the potential here, all the points inside this big box have equal potential. That's what you're saying. Well, actually, when you start to sum up in the method I described earlier, what you're actually saying is the effect from these points here are the same inside all the points here. But the effects from these points here is not the same for each of these points because you're calculating them directly. So when you sum up the answer from this far field with the near field, you get different values for each of these points here because of this side calculation, because you're adding to the answer from here, the answer from here. So when you combine the two answers, each point will have a different number in it because of this side effect. So when you actually do the hands-on session coding, today we'll also try to code this one where we have a deeper tree. Now, it might become a bit tricky how to retrieve the information of these boxes because I haven't described to you how you construct a tree structure in the computer. So maybe we won't do this deep tree thing in today's hands-on because tomorrow's lecture will actually cover how to make a tree. So I'll just introduce to you the notion of a hierarchical decomposition today and maybe not do it in the hands-on session. So, but we will do it tomorrow for sure. So now the tree looks like this. So you have points here, go to the intermediate level here, which goes to the top level here, and then across, and then goes down the tree. So now we have a multi-level FMM-like algorithm. So this is now almost a FMM. Now we can do the near-far decomposition again for the hierarchical version. So if we do the near-far, we have different types. We have 3 levels of far decomposition this time, and the near field is only a very small part here. So for the top level, we sum between these the effect on the blue box here. Now we have all these white boxes that cannot be calculated at this level. These will be handled at this level because the boxes are small enough that these can interact. We can assume that everything inside here and here can interact with this coarse approximation. So we just use smaller boxes to interact with each other. And here, the part that was left out here hasn't been calculated yet. We calculate this part using even smaller boxes. So having a hierarchy of level of boxes actually allows you to cover what has been left from the top. What your parents couldn't do, you can do here. What these parents couldn't do, the children can do here in your tree structure. And then at the bottom, there's always a level where you can't go down any deeper. Here, finally, you use the direct interaction with this direct kernel here. So by combining this technique, again, you have a constant number of points always. Although there are many, it's still a constant number of points interacting with each blue box. And you have, in total, in the whole tree, you have order n blue boxes. So it's order n blue boxes times order 1 red boxes. It's an order n calculation, even for the hierarchical version. And, well, actually, it has to be the hierarchical version to be order n. And then, if you look at how these boxes, the size of these boxes are being chosen, it's sort of like an angle, right? So say this box here is touching these 2 lines. Now, this box here, the corners are touching these 2 lines. Again, now this box here, the corners are touching these 2 lines. So you're sort of looking at and deciding how small the box should be in the form of an angle. So it's like the notion of a parsec in astrophysics. You're looking at, parsec is an angle. It's not an actual distance. You measure, celestial bodies in parsecs, but that's actually an angle. And so and the reason why that's useful in astrophysics is because the further away they are, the less you have to distinguish them. It's actually a concept that's similar to here. If the angle looks similar to you, so basically if they're far away, you can actually group them into bigger groups because to you it makes less difference. So if you're inside this box or inside this box, the error of summing them up and considering them as one thing, this error here of approximating everything as one thing, and also saying that everything that's acting on this one is the same as the one that's acting on the individuals. This equality here is accurate enough if the angle looks the same. So this is the notion of the opening angle when you decide how you interact. Because you can actually make the angle narrower to increase the accuracy. So say that you choose the angle to be narrower. What happens is, well, actually, I have a slide for the next lecture. It's going to look like this one. So I'm sort of jumping into the slide of the next lecture, but just to give you the idea of what happens when you narrow the opening angle. A 3 by 3 by 3 neighbor region is now looking like this. It gets bigger. You have more direct interactions to do. And the boxes that were this big size are now of a smaller size. And this is because you're narrowing the angle. And you can do this gradually. You don't have to immediately go to like 5 by 5 by 5. You can leave out the corners because the accuracy of this approximation is sort of a function of the distance from the center. So you want this shape of this region, the dark region, to be close to a sphere as possible. You don't want it to be a square because the corners will have the largest errors. So you want to sort of chop off the corners when you make this type of interaction list. But so this one has less approximation, but more boxes to calculate. And so should I strictly follow the time?
Yeah,
maybe we can have a 10-minute break?
Yeah.
Okay, so because I've already finished, so this is actually for the next slide. So this was the last slide of my first part, so I should finish here and then start again in 10 minutes. Okay? All right, thank you very much. Okay, welcome back. So this is the second part of today's lecture part. And I'll be talking about a continuation of this morning's lecture. So just to review, let's start again with this very simple version where you have two distant points in the box, and you gather everything, you sum everything to the center, you calculate its effect, its potential on a center point here, and then you assume that everything is equal. So the question we didn't ask this morning in the first lecture was, how accurate is the solution when we do this? So how can we make this more accurate? Or how can we measure? And of course, in the hands-on session, it's actually nice to maybe change the distance between these two boxes. It's very easy to just add one or something and make this farther away. And see what happens to the answer. Because you will be comparing the direct answer that you obtain by summing everything against everything with this equation. And you compare that with going through step 1, step 2, and step 3. And those two numbers will be different, but as you make them further and further away, they'll start becoming the same. And so what when you measure that, you'll see that when we separate them more, we get a more accurate solution, of course. So if we do something that looks like, has a larger neighbor region, when we do the well-separatedness, then the less approximation we do, it's going to be more accurate, but we have to calculate more boxes, so it's going to be slower. So, of course, there's a trade-off between speed and accuracy, but since we're using only the sum of everything, and here we're assuming that everything is equal inside the box, it's not a very accurate way to calculate. Of course, it's a good first-order approximation, and that word first-order approximation actually is very precise in terms of describing what we're doing here. But we will want to achieve better accuracy without having to calculate too many things directly. So what's the way to calculate more accurately? Okay, so suddenly I've introduced a lot of equations in this slide, but don't be afraid. I'll go through all of them very slowly. And it's not showing the bottom part of my slide, so that, yeah, maybe I'll just show it in this mode, because it's very important that you see everything in this slide. Is this too small? Yeah, maybe it's too small. Okay, I'm going to do it gradually. So first even though you can't see this here, I'll move it up in the end when we get here. Okay, so first let's just focus on this part here. So this part here that I'm showing here is actually not so different. So I'm going to go back and forth between what changed. Okay, so this is the slide we had in the morning before, where we calculate this equation.